Okay, let's dive into this. Have you ever stood in front of an incredibly lifelike robotic figure? Maybe at a theme park or in a movie, and completely forgotten you were actually looking at a machine? It's a truly magical experience. But right beneath all that realistic silicone skin, there is just a fascinating symphony of engineering happening in real time. So in this explainer, we're going to look at exactly how engineers transform raw, cold circuitry into organic, lifelike animatronics.
To really get this, we kind of have to define our terms first. Animatronics is basically the ultimate intersection of art and engineering. It's using mechatronics to simulate animate life. Think of it like this. The rigid metal framework, well, that's the skeleton, and the high-torque motors act as the muscles. But a skeleton and muscles aren't really enough to make something feel alive, right? I mean, a puppet controlled by a pre-recorded computer program is definitely impressive, but it's totally blind to the world around it. And that brings us to the core question driving this explainer today. What kind of sensors can I actually use with my animatronic device? How exactly do we give these machines the ability to dynamically perceive, react, and interact with their environment in real time? How does a machine literally know that you are standing right in front of it?
Here is how we're going to break it all down. We're going to build an animatronic system by system. First, bringing machines to life. Then, sensing the unseen. Number 3, motion and navigation. 4, the robot nervous system. And finally, protecting the puppet.
All right, let's kick things off with Section 1, bringing machines to life, the foundational elements of robotic perception. So the crucial point is, how do we actually ground these abstract electrical concepts into physical reality? Well, it really starts with how robots process light. You see, when we look at a normal light bulb, we just see uniform brightness, but it's actually made up of different energy bands. Visible light sits right in the middle, but animatronics often utilize the extreme ends. Over on the left is low-energy infrared, literally meaning below red, which we actually feel as heat. And on the right, high-energy ultraviolet, which is so energetic it forces certain materials to physically glow in the dark. By tuning sensors to these invisible bands, a machine can perceive elements of a room that we humans completely miss.
Moving on to Section 2, sensing the unseen, giving the machine its eyes and spatial awareness.
To give our machine these eyes, without it actually having to touch anything, engineers rely on a sheer variety of non-touch sensors. Passive infrared, or PIR sensors, are those incredibly common, inexpensive detectors that look for human body heat. They're absolutely perfect for a simple trigger when someone just walks past. Or consider ultrasonic distance sensors. These actually mimic a bat's echolocation. They send out high-frequency sound waves to measure exactly how far away an approaching object is. But if you are looking for ultimate spatial awareness, you need LiDAR, light detection and ranging. This is basically the high-tech vision of the robot. It fires off lasers and measures the exact time it takes for that light to bounce off an object and return to the receiver. It works incredibly fast, and it maps things out three-dimensionally, giving the animatronic this highly accurate, real-time map of its entire surroundings. It's wild.
Then we have FLIR, which stands for Forward-Looking Infrared. Originally, this was developed for military aircraft to navigate through blinding fog. Today, FLIR cameras assemble a video output based entirely on heat. So if you want your robotic figure to, say, lock eyes with the warmest object in a cool room, like a human guest, FLIR makes that happen instantly.
But wait, what if you want to hide your sensors completely? I mean, you definitely don't want a bulky camera lens ruining the magic of a historical figure's face, right? That's where microwave radar is just brilliant. Radar can literally see right through fabric or even the plastic housing of the animatronic itself. It uses the Doppler effect, which is the exact same principle police use to track a speeding car. It pulses electrical waves, and if the returning wave's frequency is even slightly altered, the robot knows an object is moving towards it, how fast it's moving, and from what direction. All through a solid wall? No way, right?
Now, spatial awareness isn't just about scanning the horizon. It's also about what's immediately next to the robot. Hall sensors and magnetometers act as proximity alerts for metals. For instance, a Hall sensor can detect the edge of an aluminum table, so a mobile animatronic knows to stop before it completely falls off. Similarly, a magnetometer detects steel, much like those magnetic loops buried in the street that tell a traffic light that your car is waiting at the crosswalk.
Let's move to Section 3 and see how this builds. Motion and navigation, the robot's inner ear and spatial awareness.
Okay, so we've given the robot eyes, but now it desperately needs an inner ear, basically an awareness of its own posture.
Accelerometers measure changes in speed across the X, Y, and Z axes. They tell the robot things like, hey, I am moving forward, or uh-oh, I just bumped into something. An inertial measurement unit, or IMU, takes this a whole step further by adding gyroscopes to measure orientation and angular velocity. Think of the sensor in a car that triggers a dash cam during really heavy, sudden braking. An animatronic uses an IMU to actually feel gravity. It can detect if it's leaning way too far over, or if the terrain is getting way too steep for safe operation.
Now combine that internal balance with GPS, and the possibilities absolutely explode. GPS receivers map 3D locations by talking to a whole constellation of satellites, which allows for truly autonomous movement. Just picture it, a robotic stormtrooper autonomously roaming around an amusement park. Or maybe an automated robot server navigating the incredibly complex floor plan of a busy restaurant using GPS data to move around safely without any human intervention at all.
Moving inward, we have Section 4, the robot nervous system, covering internal feedback and protective reflexes.
So what happens when a random software glitch tells a robotic arm to bend way past its physical limit? Well, without internal feedback, those powerful motors would literally tear the metal framework apart. To stop this, engineers install crucial internal hardware protections like limit switches and potentiometers. Think of limit switches as the robot's basic pain receptors. They're these physical microswitches placed at the very edge of a joint's range of motion. If the metal arm hits that switch, boom, the system instantly cuts power to the motor. Potentiometers and rotary encoders are even smarter. They're essentially joint monitors that constantly track the exact angle of every single limb, ensuring the computer always knows precisely where the robot's hand or head is positioned at any given millisecond.
Which brings us to Section 5, protecting the puppet, saving the delicate silicone skin.
This internal nervous system we just talked about is absolutely critical to protect the incredibly expensive, heavy silicone skins that cover the machine. And this brilliantly illustrates the dynamic reflex sequence required to keep that skin intact. Imagine this scenario. First, the silicone skin accidentally catches or binds in a joint. Second, because that joint is stuck, the motor pushes even harder, causing a massive spike in electrical current. Third, a specialized current sensor instantly detects this abnormal power draw. And finally, the system shuts down the motor entirely before the sheer force tears the silicone or burns out the servo. Honestly, it's a total lifesaver for both the hardware and the budget.
Another massive part of protecting the illusion is keeping things quiet. In the past, those mechanical limit switches we talked about earlier caused a lot of problems. They physically click, which is loud, and because they rely on physical contact, they naturally wear out over time. Today, modern animatronics use magnetic Hall effect sensors instead. These use tiny little magnets to detect joint limits without ever actually touching. They are entirely frictionless, totally immune to wear and tear, and most importantly, they are completely silent, ensuring the puppet's movements remain pristine and organically quiet.
Finally, we can use sensors not just for protection, but for real connection. Traditional clicky switches just feel cold and robotic, but capacitive touch sensors, those can be completely hidden right under a puppet's faux fur or silicone. If a human guest gently strokes the creature's head, the capacitive sensor detects the human touch right through the fur, triggering the animatronic to lean into the hand naturally, organically. Or, if a human puppeteer is controlling the robot live, they might wear a glove lined with flex sensors. As the human bends their fingers, the flex sensors track the exact curvature, instantly translating that subtle human movement into breathtakingly fluid facial or jaw expressions on the animatronic. The level of artistry is just incredible.
It really is an incredible synthesis of disciplines. We've taken raw electricity, layered it with light spectrums, radar, gyroscopes, and current sensors, and wrapped the whole shebang in silicone to create something that actually breathes, reacts, and interacts. Which leaves us with a pretty profound question. As circuits and biological modeling continue to merge, and these sensor networks become more and more sophisticated, how close will we actually get to building machines that don't just simulate life, but genuinely feel alive? It's definitely something to think about the next time an animatronic locks eyes with you. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.